Hello everyone and welcome back to another video with Leah. Today I'm going to be going over a chemistry exam review that is going to include practice questions and include topics such as titration, balancing equations, limiting reactant, acid and base, gas forming reactions, molarity, etc. I really hope you enjoy this video. If you do, remember to comment down below and subscribe. How many moles of hydrogen gas are needed to produce 2.64 moles of ammonia in the reaction below? Luckily enough for us, this reaction is balanced. So we can go ahead and start our stoichiometry for this. So remember, we have this thing that goes like grams of A to moles of A to moles of B to grams of B. Now, because we are only dealing with moles of ammonia and moles of hydrogen, right? We are going to only be dealing with this part of the conversion map. Okay, so we can put moles of A as moles of ammonia, okay, which is going to be 2.64. And this needs to be converted to moles of hydrogen gas, so H2. Okay, and we don't know the number of moles of H2, which is what we want to figure out. So here we go. 2.64 moles of ammonia. Alright, and so to cancel out moles of ammonia, I'm going to put that unit on the bottom. And we know that according to our balanced equation, we have 2 moles of ammonia for every 3 moles of hydrogen gas. Because moles of ammonia are on the top and bottom, I can cancel out this unit, leaving me with moles of hydrogen gas. So now that I have the unit that I want, I can just multiply straight across. This is going to be giving 3.96 moles of hydrogen gas. Okay, so this is the number of moles that we need to produce the 2.64 moles of ammonia. How many grams of carbon dioxide are produced in combustion when 203.54 grams of C3H8, which is called propane, and 41.09 grams of oxygen gas react, which is the limiting reactant? Alright, so we are given this information and we know that we need to write out the reaction, right? Because whenever we are dealing with limiting reactant problems and stoichiometry, we know that we need to have the balanced equation ready for us. Okay, so for combustion, we are going to have a hydrocarbon, in this case propane. Remember, a hydrocarbon is simply carbon and hydrogen and maybe oxygen, okay? And this is going to be added to oxygen gas because things are going to burn in oxygen gas. And the products for this are going to be carbon dioxide and water. Okay, these are the products of a combustion reaction. Alright, so now that we have our reactants and products, we can go ahead and balance this equation, because balancing the equation is going to be important for limiting reactant problems, as well as stoichiometry problems. Alright, so to balance an equation, we simply count the number of each element on each side. So we have carbon, we have hydrogen, and we have oxygen. We have them on both sides. Now on the left side, we have 3 carbons, 8 hydrogens, and 2 oxygens. On the right side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Right, 2 right here, and another oxygen right here. Now we see here that according to our balancing equation tips, we want to balance the element that appears once on each side, which is carbon and hydrogen. Okay, so we can balance carbon first by putting a 3 right here. That means we have 3 carbons now, and we have 7 oxygens. Okay, so 3 times 2 is 6, plus 1 is going to be 7. So now our carbons are balanced. Now let's try to balance our oxygens. For this, we can put a 4 right here. So 4 times 2 is 8. And we're going to have to recount our oxygens as well. So we have 4 oxygens here, and we have 6 oxygens here. So that's going to be 10 oxygens. Now we can just put a 5 right here. Okay, so that we have 5 times 2 is 10 oxygens. So now our balanced equation is 1 mole of C3H8 plus 5 moles of oxygen gas to yield 3 moles of carbon dioxide and 4 moles of water. Alright, so now we can get into the information that they are giving us here. So how many grams of carbon dioxide are going to be made? Okay, so we know that we are going to deal with this map here. So grams of A, 2 moles of A, 2 moles of B, 2 grams of B. Okay, and so we start out, let's do this one first. So 203.54 grams of propane. So starting out with grams, we'll have A as propane. Okay, we're going to start here, and next we're going to go to our moles of propane. To convert this to moles of propane, we need to use the molar mass. Okay, so to cancel out the grams here, we put the grams of propane on the bottom of the new fraction. Okay, and we have this 1 mole of the propane. And in this way, the unit can cancel out. Now, this number of grams is going to be the number of grams of propane in 1 mole, so the molar mass. And this number of grams is going to be 44.11. Okay, so that's going to be the mass from 3 carbons and 8 hydrogens. Next, we want to convert this moles of propane to moles of B, so the moles of carbon dioxide. So moles of propane will go on the bottom, and moles of carbon dioxide will go on top. Now, when we are converting moles of one thing to moles of another thing, we're going to use the balanced equation, which is going to tell us the ratio between carbon dioxide and propane. So we see here that with 1 mole of propane, we have 3 moles of carbon dioxide. Okay, so I'm just going to plug in the numbers right here. Now our moles of propane are going to cancel out because one is on the top and the other is on the bottom. Lastly, we're going to go from moles of carbon dioxide to grams of carbon dioxide. To cancel out moles of carbon dioxide, I will put that on the bottom. And we are going to convert to grams of carbon dioxide, which I will put on top. Now, remember, when we are dealing with grams and moles in stoichiometry of the same substance, in this case carbon dioxide, we're going to use the molar mass. So how many grams of carbon dioxide are in 1 mole of carbon dioxide? Well, this is going to be equal to 44.01. Okay, and now that I can cancel out moles of carbon dioxide, I see that I'm left with grams of carbon dioxide. And now I can just multiply straight across. This is going to give me 609.24 rounded to the nearest hundredth grams of CO2. Okay, so this is the amount of CO2 that can be made with this amount of propane. Okay, so this part is going to give us this. Okay, and our next step is to find how many grams of carbon dioxide can be made with this amount of oxygen gas. Again, we're going to follow the same map, so grams of A, which is going to be the oxygen, okay, 2 moles of A, 2 moles of B, 2 grams of B. Because we cannot convert directly from grams of A to grams of B. We must go through moles. Right, so same thing, so 41.09 grams of oxygen gas. And we need to convert this to moles of oxygen gas. So to do this, we're going to cancel out the grams of oxygen, and we want moles of oxygen gas. Okay, so we're going to be using the molar mass, so how many grams of oxygen are there in 1 mole of oxygen? That'll be 32 grams, and then these cancel out. Now we want to go from moles of oxygen to moles of carbon dioxide. So canceling out moles of oxygen, that means we'll put this part on the bottom, and we'll have moles of what we want to go to, which is carbon dioxide, on the top. Okay, so now we look at the mole ratio. So the mole ratio is that if I have 5 moles of oxygen gas, then I'm going to produce 3 moles of carbon dioxide. Okay, so remember, when you're converting moles to moles of different things, you're going to look at the balanced equation. Okay, so now moles of oxygen can cancel out. Next, we're going to go from moles of carbon dioxide to grams of carbon dioxide. Putting moles of carbon dioxide on the bottom allows me to cancel. Okay, one is on the top and one is on the bottom. And remember, here we're going to use the molar mass of carbon dioxide. So we're going to have in 1 mole of carbon dioxide, Well, we know that there are going to be 44.01 grams of carbon dioxide. Okay, and now I'm going to multiply straight across because I'm with the unit that I want. Grams of carbon dioxide. This is going to give me 33.91 grams of carbon dioxide. Alright, so here we have that with this number of grams of propane, I can make this number of grams of carbon dioxide, and with 41.09 grams of oxygen gas, I can make this number of grams of carbon dioxide. Now we see here that I can make less carbon dioxide given this number of grams of oxygen gas, which means that oxygen gas will be the limiting reactant for this question. What is the net ionic equation for the reaction of lead to nitrate and potassium hydroxide in water? Alright, so for a net ionic equation, remember, we're going to just have the equation without the spectator ions, okay? So let's go ahead and write here. So lead 2 is this and a nitrate ion. Okay, so lead has a positive 2 charge, right, given by this Roman numeral, and nitrate ion has a negative 1 charge. Now we want the lead 2 nitrate compound to be neutral, so that means we need 2 nitrates. Next we have, and I'll just add the AQ for practice. Next we're going to have we have potassium hydroxide. So this is of K plus and a hydroxide ion, so positive 1 and negative 1, so just one of each together. You can also remember that potassium hydroxide is a strong base. Next we're going to write the products of this reaction. This is going to be a double displacement reaction, okay? So outer things go together and inner things go together. Okay, so we have lead 2 hydroxide, which we need 2 hydroxide ions because lead has a positive 2 charge and hydroxide has a negative 1 charge. Okay, and then we're going to add this to potassium nitrate. Okay, so 1 potassium and 1 nitrate ion, because potassium has a positive 1 charge and nitrate has a negative 1 charge. Next, we need to balance this equation. Okay, and these little AQ and S and AQ, well, these are just determined by a solubility table or chart. You can easily find one online just by typing in solubility chart or table into the search bar. Next, because we are doing a net ionic equation problem, we need to balance this equation. Alright, so we're going to count the number of each element on each side, keeping polyatomic ions as a unit. Okay, so we have 1 lead on this side, 2 nitrates, 1 potassium, and 1 hydroxide. We'll do the same for the right side. So we have 1 lead, 1 nitrate, 1 potassium, and 2 hydroxides. In order to balance the hydroxide, right, we can just put a 2 right here, which means that we'll have 2 potassiums and 2 hydroxides. Next, we can put 2 right here to make 2 potassiums and 2 nitrates. Now our equation is balanced. Okay, and so currently this will be called the molecular equation. Generally, this is called the molecular equation, and next our job is to find the complete ionic equation. Okay, so we're going to break up into ions of things that have a little AQ at the end, okay? And those are going to be dissolved in this water. So Pb, we're going to write its charge, plus 2. We're going to write the 2 nitrates here. Notice how we just write the subscript as a coefficient, okay? Next, and all these are going to have the little AQ. Okay, it just takes up a lot of space. Okay, and then next we have potassium hydroxide, which is soluble in water. So we're going to have 2 of these, plus 2 hydroxides. And then we're going to go onto the product side and do the same thing. Now, we're not going to break up the lead 2 hydroxide because it is insoluble. It is a solid. Okay, so it's just going to stay together. And that's going to be added to 2 potassium, positive 1 charge, and 2 nitrates. Okay, each with a negative 1 charge. Okay, and both of these are going to have the little AQ. Now we're going to make the net ionic equation by crossing out the spectator ions. Now the spectator ions appear the same on both sides. So for example, nitrate is going to be one of them. Nitrate is a spectator ion, as is potassium. Okay, they both appear for potassium as 2 K plus on each side. Notice, however, that lead and the hydroxide do not appear the same on both sides. On the left side, Pb plus 2 appears, and on the right side, Pb is combined with OH2. Okay, so this right here, right, the equation that doesn't have the spectator ions is called our net ionic equation. What are the products when iron 2 carbonate reacts with hydrochloric acid? This is a gas-forming reaction problem, and as we see here, we're just going to use this little chart for reference. Okay, so we have iron and carbonate ion is going to react with hydrochloric acid. Now when we put these two together, we want a neutral compound, so we'll just have one of each. The positive 2 and negative 2 will cancel out. Now we're going to add this to hydrochloric acid, HCl. You would agree that iron is a metal, and carbonate, well, we see carbonate right here. And we see here that when a metal is combined with carbonate and added to an acid, we get these products. Okay, a metal salt plus carbon dioxide and water. So we're going to have this metal salt, okay, FeCl2. We're also going to produce some carbon dioxide, and we're going to get some water as well. Okay, so the metal salt is just the metal combined with the anion from the acid. Okay, and then we know that the formula for carbon dioxide and water are as follows. So these are the products when iron 2 carbonate reacts with hydrochloric acid. Okay, you're simply going to look at the chart and say, okay, I have a metal and a carbonate. Where does that fit in? It fits in right here. Okay, and I have an acid, so I have this one. And then you just see the gas that's produced and the other products. What is the net ionic reaction for when hydrochloric acid and lithium hydroxide react? So hydrochloric acid is a strong acid, HCl. Okay, it's aqueous in water. And we're going to add this to lithium hydroxide, LiOH. Okay, this is a strong acid, and this is a strong base. When you combine this acid and base, you're going to get water and a salt. And the salt is going to be the combination of lithium and chlorine. Alright, so we know that in the solution, we're going to have on the left side H plus Cl minus plus Li plus added to OH minus to yield H2O. We're going to keep H2O together because, as you know, just liquid water is not going to dissolve in liquid water. Okay, it's just going to stay the same. Plus lithium plus added to chlorine minus. Okay, and these, the ones that are separated into ions, are going to have the little AQ. Alright, and now we're going to cross out these spectator ions. So if they look like an ion on one side, they should look like an ion on the other side. These are going to be the chloride ion, lithium ion, okay, leaving us with H plus a hydroxide to yield water in liquid form. Okay, so this is going to be the net ionic reaction when a strong base and a strong acid react. Right, so here we have a redox reaction question. Okay, and we want to know which species was oxidized, reduced, which one lost or gained electrons, and which one was the oxidizing agent and which one was the reducing agent. Okay, and we also want to write the half reactions for the oxidized and reduced species. Okay, and we're going to use this reaction. And it's important to know for redox reactions that you have to balance the equation, okay, so that the electron transfer can be equal. Okay, and so we see that this reaction is balanced. We have 1 zinc on each side, we have 2 hydrogens on each side, and we also have 2 chlorines on each side. So the next step is to find the oxidation numbers of each element in this reaction. Okay, so we'll start with zinc here. Zinc is standing alone in the reaction, so its oxidation number is going to be 0. Next we go on to HCl. Chlorine is going to have a -1 charge because it is a halogen, and hydrogen is going to have a +1 oxidation number. Next we're going to go over to the product side. And we see here that the halogen, chlorine, is going to remain a -1 charge for each one. However, because there are 2 chlorines, a -2 oxidation number is going to be the total for the chlorines. Now, zinc to chloride has to be neutral. Okay, so the entire thing has to be 0. And already we have a -2 involved, meaning that something plus -2 must give us 0. That means that zinc must be +2 Okay, and because there's only one zinc atom in this compound, zinc has a positive 2 oxidation number. Next we have H2. So this is just 2 hydrogen atoms, and they're just standing alone. So each hydrogen atom here is going to have a 0 oxidation number. Okay, now we need to start answering our questions. So in this oxidation numbers, right, we see that zinc went from 0 to positive 2. It went this way, which means that it had an increase, okay, in oxidation number. And I'm just going to put OX and this for oxidation number. So if something has an increase in oxidation number, that means that it was oxidized. And something that is oxidized has lost electrons. Okay, I'll put E- for electrons. And lastly, something that was oxidized must have caused the reduction of another thing. So we'll call this one the reducing agent. Next, we see that hydrogen, okay, went from a positive 1 oxidation number to 0 oxidation number. Okay, and if it goes this way, it was a decrease in oxidation number. And a decrease in oxidation number indicates reduction, so hydrogen was reduced. And if something is reduced, it had to have gained electrons, right? It had to have gained more negative charge so that it could go more negative in its oxidation number. And something that was reduced is called the oxidizing agent, right? It had to have caused the oxidation of the other thing. Alright, and so now let's write the half reactions for zinc and hydrogen. Alright, so for zinc, we are going to have the neutral zinc atom, and this is going to be a loss of electrons, which means that we're going to write the 2 electrons that were lost on the product side. And this makes sense because this zinc over here had to have lost 2 electrons so that it could make zinc plus 2. Now for hydrogen, right, we are going to write that the 2 hydrogens here plus 2 electrons resulted in just a neutral H atom, okay? And we'll have 2 of them there because there are 2 right here. If 2 electrons were gained for hydrogen, then that would make their positive charge go away for each atom, which would give us just 2 atoms of hydrogen with a 0 for their oxidation number. What is the percent yield if 2.03 moles of oxygen produce 39.99 grams of carbon dioxide? Alright, so the first step in this would be to balance the equation, but luckily for us, the equation here is already balanced. Now, we know that percent yield is equal to the actual yield divided by the theoretical yield. And this fraction will be times 100, right, and this will give us our percent. Now, we have to know that the actual yield is going to be this number here, okay? And we have to know that the theoretical yield is just the stoichiometric yield, right? It's just going to be what we get from stoichiometry. So because we're going to use this equation and we are already given the actual yield, we need to find the theoretical yield, okay, from stoichiometry. So that means we need to find how many grams of carbon dioxide should be made when 2.03 moles of oxygen are input. So we're going to go from moles of oxygen gas to moles of carbon dioxide to grams of carbon dioxide. That is our map from here to here because we cannot go directly from moles of oxygen to grams of carbon dioxide. We must go through moles of carbon dioxide first. So we're going to start out with 2.03 moles of oxygen. And in the next fraction, we want to cancel out moles of oxygen, so we'll put that unit on the bottom. And on the top, we'll have our next one, our moles of carbon dioxide. Okay, and so when we have moles of one thing to moles of a different thing, we're going to use the balanced equation and see the mole ratio there. So we see here that for every 2 moles of oxygen gas, we have 1 mole of CO2. Okay. And now, because moles of oxygen are on the top and bottom, this unit cancels out. Next, we're going to go from moles of carbon dioxide to grams of carbon dioxide. This conversion is going to use the molar mass of carbon dioxide. So here in our new fraction, we want to cancel out moles of carbon dioxide, so we'll put that unit on the bottom. And on top, we'll have grams of carbon dioxide. Now the molar mass of carbon dioxide is the atomic weight of carbon plus 2 oxygens. And this is going to be 44.01 grams per 1 mole of carbon dioxide. Now that we have moles of carbon dioxide on the top and bottom, we can cancel out that unit, leaving us with grams of carbon dioxide. We know this is the unit that we want, so now we can just multiply straight across. This will give 44.67 grams of carbon dioxide. Okay, and this is going to be our theoretical yield, what we get from stoichiometry. Now we're going to plug in our values. So our percent yield is going to be equal to the actual yield of 39.99 grams of carbon dioxide divided by 44.67 grams of carbon dioxide times 100. Now notice here we have the unit of grams of carbon dioxide on the top and bottom, so we're just going to go ahead and cancel that out. This is going to turn out to be 89.52%, rounded to the nearest hundredth. A beaker with 341.8 ml of 0.57 m sulfuric acid was in the laboratory. What is the number of grams of sulfuric acid present in the beaker? Alright, so now we are dealing with a molarity problem, so we will recall that m, which will be molarity, is equal to moles over liters. Okay, liters is volume. We have a volume that is given in milliliters, okay, which can be converted into liters by moving the decimal place over to the left 3 places, or simply dividing by 1000. Okay, and our moles of sulfuric acid need to be found in order for us to find grams. So what we're going to do for this question is to find the moles of sulfuric acid, which has a formula of H2SO4, and then with this we're going to use the molar mass in order to find the number of grams of sulfuric acid. Okay, and so what we need to do here is find the moles first, which we can do by using this equation. So we have that the molarity is 0.57 m, okay, and this is going to be equal to the moles, currently we don't know it, so I'll just put an x here, divided by the liters, which is 0.3418 liters, okay, and so to find x, we're just going to multiply both sides by 0.3418 liters. And so liters is going to cancel out on the right side, leaving us with x equal to a certain value. This is going to be 0.195, okay, and this is going to be the number of moles of sulfuric acid. Now that we have our number of moles of sulfuric acid, we can convert that to grams of sulfuric acid. Okay, so 0.195 moles of the acid. Well, we need to use the molar mass. So in order to cancel out moles, we're going to put the moles of the acid on the bottom and the grams on top, so that the moles can cancel out. Using the molar mass, we know that in 1 mole of this acid, we have 98.08 grams of the acid. And now we're just going to multiply straight across. This is going to give us 19.126 grams of sulfuric acid. So for this question, we know if we have molarity and we have the volume, we need to find the number of moles. Next, because it wants grams, we need to convert moles of that compound to grams of that compound using the molar mass. If there are 6.23 grams of oxalic acid, C2H2O4, placed into water to create a 300 ml solution, what is the concentration? Okay. So first thing that stands out here is that we're dealing with concentration, aka molarity. Okay, so I'll write the equation for molarity here. M is going to be equal to moles over liters. Okay, moles divided by liters. And we have here that we have 6.23 grams of this acid, and the volume here is going to be this. Okay, so what we need to do here is we need to convert the grams of this acid to moles of the acid, right? So we can have this value, and we need to convert this value of ml, milliliters, into liters so that we have this value. Okay, so let's first convert the grams to the moles of the acid. Okay, so when we're doing this, we want to cancel out the grams. So grams of this acid will go on the bottom, so we can cancel out this unit, and moles will go on top. Now when we are dealing with grams and moles for this question, we need to use the molar mass. And the molar mass here is that in 1 mole of this acid, we have 90.04 grams of the acid. And now the grams of oxalic acid cancel out. So now we have the problem that goes 6.23 divided by 90.04. This would give us 0.069, and that will be in moles of the acid. Okay, so now we have the moles, so we can start writing our equation. Our number of moles is going to be 0.069, and now we need to find liters. Okay, so we know that we have 300 milliliters, however we need to convert this to liters. Okay, so we're going to cancel out milliliters, so we'll put that unit on the bottom, and we'll put liters on top. Okay, so milliliters can cancel out. Now, we need to use the conversion factor between milliliters and liters, and that conversion factor says that if we have 1 liter, we have 1,000 milliliters, and that will give us 0.3 liters. Okay, so we'll plug that up here. And now we will be able to find our molarity by dividing 0.069 by 0.3. This gives a value of 0.23 m, okay, moles per liter. So instead of giving us the values moles and liters so we could directly put them into the equation, we had to do a little bit of extra work to first convert the number of grams to moles, okay, because this equation doesn't accept grams, okay, and we had to convert this number of milliliters into liters so that we could put it into the equation. Because the equation doesn't allow milliliters, it only allows liters. What is the pH of a 0.0061 m solution? Okay, so the concentration is 0.0061 moles per liter. Okay, this is the molarity, or the concentration. Now, if we want to find pH, we know that pH is going to be equal to negative log of whatever that concentration is. Okay, and in this case, we'll just write the hydronium ion in here. Okay, it'll just be the concentration. So if you see H plus or H3O plus, you think of the acid and you think of concentration. The brackets indicate concentration. Okay, so we're going to plug in our numbers. So pH is going to be equal to negative log of concentration, which we were given here, which is 0.0061. And we will calculate this in order to get a pH. The answer here will be 2.21 as our pH. What is the concentration of a solution with pH 3.6? Alright, so another thing, we're going to deal with pH and concentration. Okay, and when we do this, we need to find concentration now. So concentration, also written as the brackets that have the hydronium ion or the H plus ion, will be equal to 10 to the negative pH. So let's start putting in our numbers. So the concentration is going to be equal to 10 to the negative value of the pH, so negative 3.6. The answer here is going to be 0.00025 as our concentration. The key here is to know the equations to find concentration and to find pH. Solution A has a pH of 1.5 and solution B has a pH of 1.39. Which solution has a higher hydronium concentration? Alright, so we want to find concentration. Which one has the higher one? And remember, when we are finding concentration, okay, that's going to be equal to 10 to the negative pH. Given the pH values, we need to convert to concentration. So for solution A, okay, this is going to have a concentration of 10 to the negative 1.5. Solution B is going to have a concentration of 10 to the negative 1.39. Solution A has a concentration of 0.0316, and solution B has a concentration of 0.0407. Strontium hydroxide and sulfuric acid react and produce water and a salt. What number of grams of this base will react with this much of the acid with concentrations given? So here we have to write the balanced equation. Okay, so we have strontium hydroxide and we have sulfuric acid. and this is going to make water and a salt. That salt is going to be made of the cation of the base and the anion of the acid. And now we are going to balance the equation by putting a 2 right here so we can balance out the hydrogens and oxygens. Alright, and now we can start answering the question. Okay, so we can figure out how many moles were here by converting 102 grams of sulfuric acid to moles of sulfuric acid. Okay, so I wrote out my units in the new fraction so that we can cancel out grams of sulfuric acid. For this, we're going to be using the molar mass of sulfuric acid. So in 1 mole of sulfuric acid, we have 98.08 grams. And now we just divide so we can find the number of moles. The number of moles here will be equal to 1.04 moles of sulfuric acid. Now that we know the number of moles of acid that reacted, we can use the mole ratio given in the balanced equation here to find how many moles of the base would have had to react. And then once we find the moles of the base, we can find the grams of the base. Alright, and so if we have 1.04 moles of acid, we use the mole ratio to figure out how many moles of base would have reacted. So in this, we're going to be canceling out the moles of acid and converting this to moles of the base. So this is the number of moles of strontium hydroxide that had to have reacted. And now we can convert this number of moles into grams of strontium hydroxide. Okay, so we'll write our new fraction. So we're going to use the molar mass, and we're going to be canceling out the number of moles of strontium hydroxide. Okay, so in 1 mole of strontium hydroxide, there's a certain number of grams, and that number of grams will be 121.64. Okay, so now moles of this base cancel out, and we're left with this multiplication. This is going to be 126.51 grams of strontium hydroxide. How many milliliters of water must be added to dilute an originally 0.74 m solution to a concentration of 0.625 m if the original volume was 340 milliliters? Okay, so this one we're going to use the equation m1 times v1 is equal to m2 times v2. The initial molarity times the initial volume should equal the final volume times the final molarity. First, we need to find the final volume, and then from there we can find the difference so that we can find how many milliliters of water had to be added. Okay, so for initial molarity, we have 0.74 times the volume, the initial volume, which was 340 milliliters, and this will be equal to the final concentration, so 0.625, times the final volume, V2, which we don't know, so we'll just keep it as the letter here. Now to get V2 by itself, we're going to divide both sides by 0.625 m. It will cancel out on this side, and on the left side, we will have the molarity unit cancel out, leaving us with milliliters. This gives 402.56 milliliters for V2. So V2 is the ending volume. Okay, so at first we had an initial volume of 340 ml, and then we had a final volume of 402.56 ml. And we want to know how much water was added so that we could get the final volume. So all we're going to do here is find the difference. Okay, so 402.56 minus 340. So in the end, we get 62.56 ml. And this is the number of milliliters of water that we had to add to get to the final volume. If 0.33 grams of 0.025 m hydrobromic acid react, what volume of 0.16 m of lithium hydroxide will react? Right, the final answer in ml, milliliters. Alright, so we want to know the volume of the base that will react given this information for the acid. And so we need to recall that molarity is equal to moles over liters. Okay, and we know that there are 0.33 grams of the acid, HBr. we can convert this to moles of HBr, and then see the mole ratio so that we can see how many moles of lithium hydroxide had to have reacted, and then plug that into the molarity equation to find volume, because we already know the concentration of the base. Okay, so first let's convert 0.33 grams of the acid into moles of the acid. Okay, so we want to cancel out grams, so we'll put grams of HBr on the bottom and moles of HBr on the top, so that grams can cancel out, because one's on the top and one's on the bottom. Now we're going to use the molar mass of HBr, so in 1 mole of it, there are 80.91 grams of it. And this is going to give 0.004 moles of HBr. Now we're going to see how many moles of the base had to have reacted. Okay, so we're going to be canceling out the moles of the acid, so we'll put that unit on the bottom. And we'll put the moles of base on the top, lithium hydroxide. Okay, and so we see here that the mole ratio is 1 to 1 in the balanced equation. So we'll put 1 here and 1 here. Okay, and that means that 0.004 times 1 is just 0.004, and now this will be in moles of base. So this is the number of moles of lithium hydroxide that had to have reacted. Now we want to find the volume of the base that reacted. And so we know that using this equation, we can find the volume, okay? And so we can plug in the values we know. We know the molarity, which is 0.16, and that will be equal to the moles, so 0.004, divided by the liters, which is unknown, so we'll just keep it as L. From here, we can multiply both sides by L, okay, to cancel out L on the right side. And so here we have this equation. Now we can divide both sides by 0.16 to get our answer. The answer here is that 0.025 liters had to have reacted. Now, because we want this answer in milliliters, right, we have to just move the decimal place over 3 places to get milliliters. 1, 2, 3. Okay, and so we have 25 ml as our final answer.